Hello everyone, welcome to lesson 3, the last and final lesson of the week. And now we're going to be learning about sea level change in civilization. So before we're looking at ice cores in civilization. Now we're going to be looking at sea levels, how they change and how they impact civilization. So at the peak of the last ice age, about 26,000 years ago, there was so much ice on land in the form of continental glaciers that the level of the ocean was almost 125 meters or 400 feet lower than it is today, which is a lot lower. That's a lot lower. That's a lot. 400 feet? That's a ton. So much continental shelf area now offshore was exposed that the world had 25% more land. When the ice age ended about 15,000 years ago, temperatures rose, glaciers melted, and the sea level started to rise. Permanent human civilizations began just 11,000 years ago, partly because global temperatures warmed and stabilized, allowing for the beginnings of agriculture. And agriculture was really the start of civilization as we know it. So we're going to look at glaciers and how when glaciers melted, sea levels rose. So let's take a look at this graphic. So this is post-glacial sea level rise. So a sea level rise of 125 meters can cause shorelines to advance inland hundreds of or thousands of kilometers. So this is showing us glaciers all over the world. So we have glaciers in Australia and in Brazil and Jamaica, and this is in Africa. And we're kind of seeing a trend where it's all kind of following the same thing. So this is how many thousands of years ago, and this is the change in sea level. So as we see, a really long time ago, so 22,000 years ago, we can see that the sea level was about 140 meters different. So that's a huge difference. It's a huge difference. But that's kind of like an outlier. For most of it, it's about here, which is about like 125. So we can kind of see that. So looking at this, so the x-axis is the thousands of years ago, and our y-axis is the change in sea level. So as we're looking at this graph, we're seeing that the oceans have rose significantly. And something that's really interesting here is we have this period where the oceans are staying relatively pretty calm, pretty much the same. So global sea levels and shorelines have stayed remarkably stable over the past 6,000 years, allowing the establishment of large permanent coastal communities. And if we think about the great civilizations of the earth, most big great civilizations are coastal. They take place by the ocean because it provides a lot of resources. We can also look at this kind of like period where things are rapidly increasing. So at the end of the last ice age, the global average temperature rose 8 degrees Celsius. That's a lot. And glaciers rapidly melted. Global sea levels rose more than 120 meters or 400 feet. So that's a ton of flooding. A ton of tumultuous activity going on in the planet, and probably a scary time to be a human. That's just a lot of change going on. So, very interesting. Okay. We're going to look at melting ice and rising sea levels. sea levels started to rise about 200 years ago. So if we look back at this graphic, we're seeing very relatively stable things, okay? But about 200 years ago, so we're not looking at 2000, which is right here, but 200, so really, really close to here, sea levels began to rise. And why do they begin to rise? Well, they began to rise when people started burning fossil fuels and releasing carbon dioxide into the atmosphere. And this began during the Industrial Revolution. The rate of current sea level rise is more than 3 millimeters a year. It's equally due to the melting of alpine and tidewater glaciers, the melting of Antarctic and Greenland ice, and thermal expansion of ocean water as it warms. Warm water likes to stretch out, and warm water takes up more space, more volume than cool water. So it expands the water and makes it rise even faster, which is kind of interesting. As the water warms, its rate of expansion also increases because the long circulation time of deep ocean currents. The warming today is causing the rising of sea levels. Okay, so we're going to look at some more graphs. Okay, so this one we're looking at ice sheet mass loss in Greenland and Antarctica. So we're looking at how the glaciers have changed their mass, and this is in relatively short amount of time. We're just looking at 2004 to 2016 data, and we can see the trends that they're losing a lot of mass. So together, Greenland and Antarctica are now losing more than 500 billion tons of ice each year. If all glaciers melted, the sea levels would rise approximately 68 meters, which is 220 feet. And that's a lot. It's a lot of, you lose a lot of beaches, okay? And you lose in a lot of beaches. So one thing I want you to consider is, why do you think these go up and down, 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 up and down? What do you think? Well, we have seasons. In the winter, we're going to have more mass. In the summer, we're going to have less mass. More, less, more, less, more, less. And we can see that happening throughout the years. As we go from year to year, we can look at the summer, winter, summer, winter, summer, winter. And of course, we have some winters that are stronger than others and less. However, we can just see that over time, the sea ice is melting. And in Greenland, we can see it's really melting. We're losing a ton of sea ice. In Antarctica, it's not as extreme, but we can see that we're still losing a lot of sea ice overall. Okay, so this graph is looking at global mean sea level. So we're just looking at the sea level. So the mean sea level, which is the average, remember from algebra, and then we're looking at years. And this one actually goes to 2019. So remember, we're going to have in the winter less, that the sea level will drop in the winter because we have more ice, and the sea level will rise in the summer because we have less ice. So we're still going to get that summer, winter, summer, winter, summer, winter. But as we can see, just from 1993 till today, there is a significant change. It's a pretty big change. Now, if we look at this, it is in centimeters. So we're not talking about miles here or feet, but it's still, we can still see a pretty significant change, that the sea level is rising about 3.4 millimeters a year if we look at the average or the mean. of this graph. You can figure out the slope if you wanted to, but we're not going to today. So either you're welcome or I'm sorry. Okay, this is like a totally different thing, but also really cool. So sea ice isn't the only thing that can tell us about the history of Earth's climate. We can also look at things called varves. And varves are really interesting. So some lakes contain a record of annual sediment. So this is really going into the carbon cycle, right? Sedimentation, where every year we get a layer of sediment at the bottom of a lake because, pollen gets into the lake and fish die and leaves go to the bottom and everything goes to the bottom. So a varve can tell us lots of different things. It can tell us about pollen. It can tell us what plants were there and what grew and other things too. So varves, they're characterized by large particles deposited by spring storms, separated by finer particles that accumulate the rest of the year. Varves are very useful for studying regional climate over the past few thousand years. They also contain pollen, which shows the kinds and amounts of plants that grew nearby. So we can use varves to tell us what kind of plants were around and are they the same as the plants today? And where were those plants located? Have they spread? Are there more plants growing in different regions or have they declined? So we can learn about environments and ecosystems by looking at varves. Another interesting thing is to look at fossil corals. Corals grow by making calcium carbonate layers from ions in seawater. Corals are animals, they're not plants. They are animals. They're very simple animals. They're on the tissue layer of animal complexity. And they take in calcium carbonate ions from seawater to help build their structure. It's kind of like their bones. And we can analyze the density in these layers. And with that, we can figure out the temperature because the density changes as water temperature and availability of nutrients change. The composition, thickness, and color of these annual layers provide a record of ocean temperature, pH, and regional rainfall amounts. So even though these are occurring in the ocean, they're actually giving us information about how much it rained in that region for that year. So that's a lot of information we can get just by analyzing the fossils of corals. The last thing that we are going to look into that's telling us about the history of Earth's climate are tree rings. Tree rings, the width of annual tree rings vary depending on seasonal light and water availability. By comparing living trees with dead trees and with the boards used for ancient ships and houses, scientists have established a continuous tree ring record dating back more than 10,000 years. And we can actually put all of that data together and it can allow us to really effectively look at droughts throughout history. So here we have the tree ring drought reconstruction. So this is called the PDSI, or the Palmer Drought Severity Index, is a measure of ground dryness and is positive for wet times and negative for dry times. A severe drought that occurred in New York City in the 1960s, in this graph it's kind of in the 1950s, it's like the 50s to 60s, is pointed out on the graph. So we can look at some mega droughts. So in the 16th century, the 1500s, we can see there was a mega drought. So it's going into the negative territory, so we're getting a lot of drought. And in the 17th century, so in the 1600s, we had the Pueblo drought. And a little bit before the 1800s, we have El Año de Hambre. So we have another kind of little drought. The mid-19th century drought. Now, these are the ones that we know about. So the Dust Bowl. Maybe you've read The Grapes of Wrath. Maybe you haven't. That takes place during the Dust Bowl. So in the 1940s, there is a severe period of drought in the United States that took place in the middle of the United States, the Great Plains area, and places like Kansas. There just wasn't any rain. And people that lived on farms, their crops all failed. And it was so dusty because all the crops failed because people were relying on rain to water their crops, that they packed up and they headed west, and that was when there was a great migration of people to California. It was during the Dust Bowl. And a lot of people from Kansas and Oklahoma and different plain states came over to California, and a lot of them started to work on farms. And that's how maybe some of your family came in from that time. Maybe they didn't. But it's an interesting migratory period of humans in the United States because of a climate event, the Dust Bowl. It's pretty interesting. Okay, so last picture. Here's a beautiful redwood tree, my favorite kind of tree. Redwood trees can be really, really old and big. They're the tallest trees in the world. And they're also found only right here in California. So they're a very special tree. And I hope if you ever have the chance, you can go up and see them for yourself in Redwood National Park in Humboldt County, California. They are a treat. So this tree began growing in the year 550, and it was cut down in 1891. So this tree was around for a really long time. We can look at different historical events that happened during this tree's beautiful life. So we can look at Leif Erikson. He's one of the Vikings in the year 1000. He basically started to colonize Canada. We can look at the Magna Carta being signed in 1215. Joan of Arc, 1429. We can look at when Columbus, he didn't really discover America. There are people living here, but he basically went to Cuba and he took that trip there and he gave people smallpox. We can look at the Pilgrims in 1620, Declaration of Independence, 1776, Civil War, and the tree was cut down, so sad, in 1891. So we don't have as many of these beautiful, majestic, old-growth redwoods anymore. So a lot of people cut them down for timber. But we can learn so much through looking at a tree ring, and we can look at droughts, and we can look at temperatures of the earth, and how the tree had a struggle or how it just succeeded in the climate, in the temperature, in the weather of its life. So it's a really interesting thing. I also love rings. My tortoises have rings, and you can look at their rings and you can actually get some climate activity and information from tortoise rings, which is pretty interesting. So I hope you guys learned a lot this week about ice cores, about history. We did a lot of historical kind of mixing into science, which is always a fun little mashup. We learned about corals and tree rings and a lot of charts and graphs about the history of civilizations and climate on Earth. So thank you so much. Do the activities, come to the Zoom sessions. I love hearing from you guys and I miss you guys, and enjoy the rest of your week. Thank you.